Good morning. I'm very pleased to be able to present to you the progress that Quell has made with our CAR-Treg platform over the last few years. One initial question is, why Tregs? Many of you may be in oncology, and you're probably used to thinking of Tregs as being a little bit of a Machiavellian cell type that prevents your CAR-T from having the effect that you want it to have. And they do that through being profoundly suppressive. We can clearly leverage that in the world of immune dysregulation. And in actual fact, in the human body, the role that Tregs play is that they're the master modulators of the immune system. They suppress by multiple modes of action in a way that a simple biologic just can't. And through bystander suppression, they effectively coach or marshal the other cell products that are in there, telling them how to behave. And therefore, that really powerful immunosuppression is something that we get a chance to leverage in immune dysregulation more broadly. And Quell is in the lead, we believe, in a field where there's an opportunity in a one-and-done way to reset immune dysregulation across a breadth of conditions, from solid organ transplantation through autoimmunity and through the breadth of inflammation. Our leadership position, we think, is established by the breadth of the engineering platform that we have. We have a very modular engineering platform that I'll take you through. We made the decision to invest in GMP manufacturing day one, which I think has given us a good head start in terms of time through to the clinic. And actually, we've had a CTA approved for our first clinical trial. We're currently recruiting patients in that clinical trial. So hopefully moving forward towards presenting transformational data in the space. We've raised $220 million to date through the tier of investors that you see at the bottom of the page. And the management team that we've built, I think, is a really great cross-functional operating team that combines real depth of therapeutic experience alongside autologous T-cell experience and autologous T-cell manufacturing experience, clearly deep Treg biology, but also iPSC, which has come into the partnership that we've recently established with Solistic to try and drive towards an iPSC Treg product. Now let's dig briefly into the platform. Now, as I said, it's a modular platform that enables us to choose the modules that we think will best support a therapeutic response in a particular disease. And at the heart of the platform is what we call our FOXP3 phenotype lock. One of the big challenges that there is in Treg biology is that Tregs are pretty plastic. Tregs have the ability to flip from being a suppressive cell to being an attacking cell. And clearly in the world where you're using them as a therapeutic tool and you're weaponizing them with a CAR, you want to make sure that your Tregs stick as a suppressive cell and don't flip into being an attacking cell. Otherwise, you're essentially at risk of wiping out the very tissue you're looking to try and protect with your CAR-Treg. And that's precisely what the FOXP3 phenotype lock does. It locks them in a stable phenotype and stops what normally happens, which is when a Treg gets into a stressed situation, they can drift, and it prevents that drifting. Then, of course, we have either CARs or TCRs that we can employ to ensure that our cells get activated at the site of disease. And then we have what we call disease-specific therapeutic enhancements. And you can think of these as modules that give new properties to a Treg that may increase its therapeutic benefit in a particular disease state. So we have a number of different persistence modules, which is a form of synthetic biology that drives a synthetic cytokine signal into the cell. We have a number of functional enhancers that enable us to get a Treg to secrete something that perhaps it wouldn't normally secrete, or secrete more of something that it would. For example, secreting more IL-10 upon activation, secreting tissue repair factors, etc. And of course, we have a safety switch in the toolkit that enables us to take the cells out if we see an unwanted safety signal. There was one question that we had to address right at the very start, which is, what's the right starting cell type? And here there are essentially two choices. There's the choice of taking T effector cells and converting them using FOXP3 and trying to make them into suppressive cells. And you can make them into suppressive cells. We question the stability, the durability, and the potency of these cells, which led us in the direction of choosing engineered naive Tregs, which does necessitate sorting down to a smaller population of cells, but those natural naive Tregs are more stable and more functionally potent. And let me show you some data that really, I think, for us helps validate that choice. And here we're looking at a transcriptional analysis of Tregs versus T effectors, and then what happens when you add a CAR and what happens when you add FOXP3. And there's really three takeaways from this. The first is, if you look, there is daylight between the transcriptional profile of a Treg versus a T effector, with Tregs on the left and T effectors on the right. Secondly, when you transduce a T effector with a CAR and FOXP3, you do get a slight migration of the transcriptional profile of those cells, but they're still very, very close to that of a T effector. And then finally, when you look on the left-hand side and you look at the CAR Tregs with FOXP3, you can see very clearly that the transcriptional profile there really does overlap with what you see with a naive Treg. And it's our belief that gene expression matters and that ultimately function follows form. So this is something that we believe is very validating for the choice that we've made for our starting cell type. Now let me take you through some data that shows other benefits that we see associated with that FOXP3 phenotype lock that I spoke about. And here we're looking at two sets of cells in these experiments. In orange, FOXP3 phenotype locked cells, and in blue, controlled Tregs. And on the left-hand side, we're looking at an experiment where we induced stress into the cells through a cryocycle, through freeze-thaw. And what you see on the back of thawing is that you get a marked drop in a number of hallmark Treg gene expressions. So a marked drop in FOXP3, and I'll remind you, FOXP3 is the master transcription factor for a Treg. You get a drop in Helios, which is a key marker of stability, a drop in CD62 ligand, which is important for trafficking, and CTLA4, which is important for suppression. Whereas in phenotype locked cells, you do not get that drop. So in that setting, we're producing really stable Tregs. Then on the right-hand side here, we're looking at the impact that a highly inflammatory cytokine of cocktail of cytokines will make to the phenotype of these cells. And in orange, you can see very clearly that even despite that pro-inflammatory cytokine cocktail, you can see that the phenotype-locked Tregs maintain the ability to suppress through a number of different ratios of Tregs versus T effectors. But on the right, in blue, you can see pretty clearly that straightforward Tregs can actually very quickly lose the ability to suppress when they're on the background of a high degree of inflammatory markers. And importantly, you can also see in the small chart there that you get a drop in FOXP3 expression. So I think this shows very clearly that the phenotype lock that we bring, which is proprietary to Quell, is something that really does make a true difference in the phenotype. And again, we believe function follows form. And let me show you a little bit of the function. And on the left here, we're looking at the potency of the Tregs that we have. And you can see very clearly that phenotype-locked CAR Tregs show an increase in suppressive potency even over a straightforward CAR Treg. And on the right-hand side, we saw a safety benefit, which, whilst intuitive, is not something that we were looking for at the outset. If you think about how we and all companies that sort their cells will manufacture, we start with a sorting process to sort down to a population of naive Tregs, and then we transduce those cells. Now, there's not really a GMP sorting process that has 100% fidelity. You're going to get some CD4, CD8 effectors that come through into that cell product, which you then transduce. And clearly, if you transduce those cells with a CAR, you're potentially making a CAR T rather than a CAR Treg. And again, that's a potential efficacy and safety problem. But what we can show is that when we transduce cells with a CAR, they also get a copy of the FOXP3 phenotype lock. And as you can see in orange, when that happens, the ability of these CD4 and CD8 effectors to secrete the pro-inflammatory cytokines TNF-alpha and interferon gamma is markedly attenuated, which gives us great belief that we can control the impurities that you will certainly get in a cell product, as well as drive efficacy. So now let's look at the first program. And this is the preclinical data for our first program in liver transplantation. And on the left here, you can see the A2 CAR that we're actually taking into the clinic. And so clearly in the program, we'll be targeting the transplant setting where an HLA-A2 positive graft has been placed inside an A2 negative individual. And the data here is in the highly immunogenic mouse skin transplantation model. And you can see very clearly in orange that the rejection, which is a very powerful rejection in this model, is completely prevented by the CAR cells. And on the right-hand side, you can see that when we take the mice down, you can actually see in red and in blue that both CAR Tregs have infiltrated the graft and engrafted there, but also that it's recruited a number of other Tregs in the graft as well. And that's what you'd hope clearly through bystander suppression. So a really clear signal that the cells get where we want them to do and that they suppress. So now let's move and take a look at the clinical program. And this is our first program, the Liberate trial for our Quell 001 program. It's a phase 1, phase 2 trial, and the goal is to demonstrate a full durable tolerance in liver transplant patients, so removing all the immunosuppression from these patients. I think it's really important that you do remove all the immunosuppression because it's the immunosuppression that is the problem statement in these patients. It's the factor that causes malignancies, nephrotoxicity, retransplantation, etc. Now, the product candidate we're taking in is a 3-gene construct with an HLA-A2 targeting CAR, a FOXP3 phenotype lock, and a safety switch. And we're targeting patients that are 1 to 5 years after their transplant. So importantly, these are stable transplant recipients. The patients will be on a standardized immunosuppressive regimen of TAC and an mTOR. We'll leukapheresis them, manufacture, and then we'll give a really light intensity conditioning, which is very different to the types of conditioning regimens that you see in oncology. Here we're using low-dose ATG. On the cover of that, we remove the CNI, the tacrolimus, and then we infuse our cells. And then we wean that second and last immunosuppressant, the mTOR, over 6 to 7 months. First endpoint of the trial is 2 months post-cessation of all immunosuppression. And the final endpoint, the endpoint 2, is 1 year post-cessation of all immunosuppression. But even at that 2-month endpoint, all the data tells us we will see very clearly, and importantly quite bluntly, whether or not you can protect the patients from the rejection. And therefore we get a really early readout. And normally in liver transplantation, early tolerance ends up translating through to long-term tolerance. So it's something we see as a very valuable endpoint. So a very clear and early clinical endpoint. But as you can see underneath in the red circles with a B, they're biopsies. We're taking 4 biopsies through this period, and we have clearly access to a ton of peripheral blood. And through all of that, we will be able to have a very deep immune monitoring program, which will give us a very clear picture of once we infuse these cells, where do they traffic to? Do they engraft? Do they persist? Which populations of cells are they managing to marshal and control effectively, etc. So that the depth of data that we get out of here is exceptionally valuable and really useful across the rest of the pipeline. And we should have safety data from this trial in Q2 of next year. More broadly, just very briefly, the pipeline looks like this. We have a follow-on product from Quell 001. I'll remind you we're targeting the mismatch in Quell 001, which is about 25% of the liver transplant population. Quell Liver enables us to target all of those patients. We have an autoimmunity program in type 1 diabetes and a neuroinflammatory program that has the ability to target ALS, MS, and frontotemporal dementia. And in both of those, we have preclinical POCs in 2022. And I've also referred already to the Allo research program that we have ongoing in partnership with Solistic. So just to wrap up here, we've achieved a ton in 3 years since we were founded. Essentially where we are right now, we're in the clinic with that first asset. The main objective this year really is to nail that clinical trial, get to the stage that we can demonstrate in Q1 next year, Q2 next year, that we have that safety data, and then tracking around 9 to 12 months later to efficacy data. And really the data that we get from there, that deep immune monitoring data, is going to be truly valuable. And hopefully we're on path to be the first in the field to post what we believe will be transformational data with a CAR Treg. In parallel with that, obviously working on the pipeline, further platform research, and also allogeneic, and of course exploring strategic partnerships. And the presentation ends here. Thank you.